Okay, this is a video about linear programming for 2D problems and 3D problems. So this morning I wrote a code to solve a linear programming problem, and I would like to use this video to show what was done, and you could later on use it to maybe practice and understand about the process of linear programming. So in this code, because I would like to visualize the design domain, so I can only use this code to analyze a 2D problem or a 3D problem. So there are two modes. First, let's work on a 2D problem. For 2D problem, you have two variables. So in the objective function, you have two coefficients in each variable, x1 and x2. And I could have any number of constraints, linear constraints. The coefficients for each constraint are shown here in each row of this matrix A. And I need to have the same amount of constant for these inequality constraints. So what's on the right hand side of my inequality constraint will be given in this B vector, and I designed them to be a vertical vector. So basically this means x1 plus 3x2 must be smaller than or equals to 5, and so on. Of course, there could be many other possible formulations. So my code is a very simple one. I couldn't handle some other special cases, and also I can only have an initial start from 0. Okay, so this is not a powerful code for all kinds of linear programming problem, and it doesn't debug. For example, if there's a case where there's actually no solution, it doesn't debug by itself. And or some other cases, like if there are infinite number of solutions, it won't stop. You will be the code will be running until you break it. Okay, so if the problem is well defined and know the weird situations, this code should be able to solve it and show you a graphic about the iteration process. So let's move on and take a look what has been done. First, in this part, in order to calculate what's the range of my plotting, the plotting zone, how wide the plotting zone is, I did some calculation to do it. So basically, in this part, I was just trying to calculate the intercept of each constraint against each axis. So my code could automatically expand or shrink to fit whatever coefficient I give you right here. But there could be some situation where you have you have like intersection points between multiple constraints at somewhere far away. So my plotting zone needs to be larger in order to see what's going on over there. So this part was actually calculating the intersection points of multiple constraints. For a 2D problem, so this is like case 2 means I'm having a 2D problem. I basically calculate all kinds of possibilities between two different constraints, and then this code will figure if there is a point that is far away from the origin, so my plotting zone needs to be spending to in order to visualize what's going on out there. So that's my that's the part where the code could automatically decide the size of plotting. Okay. Just want to double check if it's running properly. In order to yeah, I think so. Okay, good. Okay, in the next part, I was trying to what's this about? Okay, so this is plotting the objective function and also the constraints. So for a 2D problem, once this is determining the plotting zone based on what I did earlier. I calculated the intersection point and between the constraint and the axis, and also intersection point between any two or three different constraints. So anyway, here I was able to update what would be the proper plotting zone. Okay, and let me see what I did. Okay, so I updated the plotting zone, and okay, this is the objective function. So I use symbolic, and basically this is a dot product of the coefficient C and my variables, and I use for 2D problem I use easy contour to plot out, so we can run the code up to here, and let's see what happened. Okay, so this is like the contour of the objective function, okay, and blue color representing lower value. So usually we are minimizing the function, so the solution is like far away from the origin. Okay, so let me continue here, and I also use so basically ax minus b will be the constraint. Okay, so I did that, and since the constraints are like boundaries, so you only need to draw lines, the limit state of the constraints. That's why you only need to use a easy plot to draw the boundary. So let me make a stop up to here. About here. I don't know why my Matlab recently needs some time to load, so let's wait for a couple seconds. Okay, so let me I'm not sure if it's because the internet or I don't know, because I already provide maximum memory space for Matlab. Suppose I'm giving Matlab every resources for calculation, but anyway, we just need to be patient. Okay, and if we continue, then you will see this. So basically, in this problem, I gave 3 different linear constraints, and I guess this is the region where is this the region? Yeah, I think this is the one. This is where we need to find our solution. So if you use see how the contour, observe the contour of the objective function, you will realize, okay, maybe this point is having the lowest objective function value. So that one should be the optimal. And you know, for linear programming, we will be starting from the origin. So let's take a look how the linear programming will move from intersection point to intersection point and then eventually stop. So continue. So starting from the this line 76, sorry, I basically apply the slack variables into our formulation, and also define our basic and non-basic variables. Over here, since all my constraints are inequality constraints, so I need to give a slack variable for each formulation. That's why for the constants in the objective function, will be having more zeros at the tail, and for the A matrix, we will have like a identity matrix at the right hand side of the matrix. So EYEI is the Matlab code for creating identity matrix. Okay, so this is how I get the standard linear programming format. So we could, I don't know why this is happening. It's giving me a lot of trouble. Okay. So maybe we try to avoid the debugging mode, because whenever I do it, it takes a while. So let me move forward and complete these two lines. You will tell, okay, this is my updated C vector, where you have a bunch of zeros at the for x3, x4, and x5. And for your A matrix, you can tell there will be like a identity matrix at the right hand side of this A matrix. That means we just added one slack variable for each constraint. Okay, and then to start a iteration, I have some parameters to define. So my this is my iteration 1, and I have like a flag I call converged. I set converged as 0 at the beginning, and later on, if I have convergency, I will change that to 1. So this while loop will stop. So in this while loop, first we need to calculate, we need to separate C vector and A matrix into two groups. One is for the non-basic and the other one is for the basic. So based on, basically in my coding, I didn't use any fancy code. I just follow the logic and then use the stupidest way to separate and to calculate. Okay, so for the separation, basically I check, oh, here, I have a vector named basic to represent which are the basic ones and which are the non-basic ones. So at the beginning, we know we will have a bunch of zeros in the front and a bunch of ones at the tail. So the 0 represent that corresponding variable is non-basic, and if it's 1, the corresponding variable is going to be basic. Okay, and then in my first step of the while loop, because I was checking this basic variable indicator one by one, then I could realize, okay, the ith variable is either non-basic or basic, just based on this switch checker. And then whenever I found the component, the ith component in that basic vector is 0, then I put the corresponding portion of C and A into a new vector matrix the Cn and An. And similarly, if the basic indicator is 1, that means it's a basic variable. So I will put the corresponding C component and A component into CB and AB. So CB means the basic part of C, and AB means the basic part of A. And I have a counter right here, so whenever I did it, the counter plus 1. So that's how I could easily separate C and A into two groups. Then we have, in order to plot, I will calculate what are the variables at this point. So the basic variables are non-zero, and you could actually calculate all the basic variables by the AB inverse times small b. Okay, and the basic counter here is just to assign what I calculate here to the corresponding variables. So here I have a for loop again. I start from the first one of the basic indicator, so basically a bunch of 0 and 1, and I use a switch again. If it's 0, then that corresponding vector is corresponding variable is 0. If it's 1, that means the corresponding variable is non-basic. It's basic, so it should be non-zero. If it's non-zero, then I will just assign what I just calculated to that corresponding variable. That's how I could arrange the calculation to the right corresponding variable. Okay, so this is what I have done. Then I will do a display to show what are the variables at this point. So let's make a stop here and see if we can see it. Okay, so at the beginning, because the bottom 3, the select variables, will be basic. So my x1 and x2, they are non-basic, so they are 0. Okay, so this means we are starting this linear programming process from the position of 0, 0, and our select variables are having some numbers, and we need to follow the procedure in order to change their roles, and then we could eventually get the solution. Okay, over here, this is for plotting. So whenever I know all the x, I will just plot. For 2D, you use a command of plot. For 3D, you use a command of plot3. And also, I will be drawing a line, a red line, to show, to link the previous point and the current point in order to show how the design point was moving from one position to another one. Okay, and you will be seeing it later on. So that after I finish the basic calculation of all the x and also plotting, I will then initiate the most important process of LP, which is the coefficient checking. So just follow the equation that was given in the lecture. You need to calculate this, and the result is a vector. The vectors are basically the coefficients of all those non-basic variables, and we will pick up the most negative one, so that we know when those non-basic variables increases its number, our objective function will decrease. So this is basically the coefficients of the non-basic variables in the objective function. And here is just to find which component inside this coefficient checker is the most negative one. Okay, and then the chosen one will be recorded in this variable. I name it as n to b. So that means that corresponding one will be converted from non-basic to basic. Okay, so that basically done. If this most negative one remains 0, that means I didn't found any negative coefficient, so I should converge. Then I will change the converged variable into 1 at this point. So when I move on to the second step, if that variable is still 0, I need to do it, continue to do it. If not, I will not do anything else. I will just move forward, and then supposedly the while loop will stop, because when this is 1, I don't do anything in the second step, and when you move back to the while loop, because it's 1, it will stop. Okay. So what if it's not yet converged? That means I have something in n to b. I have chosen one variable to be converted from non-basic to basic. So the next step, I will be doing the ratio test. For ratio test, we have to calculate a vector called a hat and a vector called b hat. And based on the equation of ratio test, I calculate this. And remember, we only use the raw, which is representing the one that is having the most negative coefficient. So we are only using that particular raw in a hat for this ratio test. Okay, and then over here, we will be finding if we have a smallest positive value in the ratio test. This is how I keep which one is the smallest positive one. So here could be having a bug. What if there's no smallest positive? What if when I do the ratio test here, all of them are negative or even infinite? So in fact, in that kind of situation, there's no solution. And like I said at the beginning, my code at this point doesn't debug, doesn't give any error message for that kind of problem. I only can handle a problem that is solvable. Okay, so from the ratio test, once I have it, I will keep which one will be the one that will convert from basic to non-basic. Okay, and then the last step, you basically just swap. This part is just to swap. Whatever that should be the one that converts from non-basic to basic. I convert the basic vector, the indicator, from 0 to 1. And whenever I know which one is the one from basic to non-basic, I change the value from 1 to 0. So it's just like that. And this is basically the end of the code. So when we move back to the beginning of the while loop, we will do exactly the same thing again. And then at the beginning, we will calculate what's the current value of x, and we will plot out its position. And when we will do the checker again, if it's positive, no negative, then we converge. If there's still any negative, that means we still need to continue. Okay, so let's take a look what will happen if I continue to run this code. Let's see. Okay, so over here, you can tell the code just finished the first iteration and then move on to a second iteration, and if I continue to do it, so we actually move from here to here, and we already complete the calculation of the third iteration. And then let's continue again. So it moves. Can you see that we are moving from the origin to another intersection point and then to another one until the code realizes we cannot improve anymore. So stop. Oh, actually it was stop. I accidentally restarted again. So let me just turn off those checker, and let it run the whole thing from beginning. So this is the process, and these are the solutions, all the x along the iteration. And you can see initially we start from 0, 0, then we move on to 0 and 1.666, and then